Because they have them. That's on box, isn't it? So we probably have a local copy rather than relying on box. I would imagine.
Yes, because box will probably. I mean, the internet copy will. Well, because they just had these.
Yeah. So I was going to say, if those are those on.
I don't know where that is. I don't know.
We don't want too much stuff. So those are the flash talks. So. Logan, where are the talks when you were chairing? Did you find them?
Oh,
Talks
select
Wednesday.
there, Talks Wednesday.
Okay,
Okay.
all right, because we got them on box, but we didn't really want them on box.
Here we go. Grasha. Okay, they're in
and
order.
Pascal, yeah, that's right. I've noticed that they're in order. Yeah. Ooh, that's pretty.
Let's see how this looks. Great.
Okay.
Do you want? Should I bring it down, or just leave it up there?
No, just leave it there. Yeah. And then this is a microphone that you've got to put on, and it's off at the moment, and then you just switch it on by pushing the button. So you can put it on and press the button when you're ready.
Yep. In general, I tend to not be able to. I'm one of those people that'll like.
You're a bit nervous. You're a bit.
It'll like progress 5 slides, and so.
I don't know why they don't make them with bigger buttons because it's so easy.
Or why they don't put the laser one a little bit.
Yeah, they're just too. It's too compact, isn't it?
Oh, it's off.
So yeah, you just press the button.
So you're saying this will count down?
Yeah,
you think?
I don't know who's moderating, but the moderator will start it off so that you can see. If I'm sitting there, I can't see it, but that's okay. So I guess by the time you get to 12, that thing beeps, you should have your conclusion.
If it goes to 12 and I'm not at my conclusions, I will just finish up what I'm talking about. We are mostly going to just talk about what happens if we change relative chemistry in stars and how that manifests to emissions. Because if that's not correct, then you can't do this. And I couldn't put it all together.
And the picture's nice.
This is a Things Galaxy. It's actually not super related to the talk. It's just pretty. Well, no, it's just there's H2 regions, and they're powered by massive stars that are parts of the H2 region. Because what we observe in galaxies are essentially emission lines. Sure, right? It'd be like.
Is this working?
Yeah.
Yeah. Okay. Right. Sorry. Can you please take your seats, ladies and gentlemen? The performance is about to begin, and you don't want to be late. Please sit down.
Ready? I'm ready. My microphone's on, so in theory they can hear me. I said my microphone's on, so I think they can hear me. Yes.
Okay, so our first talk in the session before lunch is going to be given by Katie Grasher, and it's on 3D imaging, spectroscopy, and models to trace the chemical history of galaxies.
Thank you. All right, everyone can hear me? Great. As I was telling one member of the SOC earlier today, when I submitted this title, an abstract, I was under the false impression I'd have about 10 hours to talk, and as it turns out I don't, so we'll see what we can do in the next 9.5 minutes. And what we're really going to focus on is looking at the role. So we've talked a lot about chemical abundances, and what we're going to talk about today is what assumptions in relative chemistry, especially if we back away from solar chemistry, how that impacts how we evolve massive stars, how this impacts how we observe our ionized H2 regions, and then how this impacts how we study galaxy evolution. So I'm coming from the Australian National University, which is notably not New Jersey. Just want to make sure that's clear. So I won't do a whole lot of background, but it's basically the practical reason why we care about massive stars is they produce indirectly or directly practically all the light we see at all wavelengths. So we have our nice, beautiful H2 regions. You know, we have star clusters. They're filled with young, hot OB stars. They emit copious amounts of ionizing radiation, which will go out, travel throughout the nearby interstellar medium. And the H2 regions that we observe, so our ionized gas emission lines, encodes the ionizing spectrum of the central star clusters from our OB stars. So H2 regions are essentially, they're rich with abundance-dependent features, so a holistic picture of both star formation at scales of individual stars and galaxy evolution at the scales of whole galaxies require both a star and ionized gas phase metallicity problem. So this is probably going to be what I feel is the most important takeaway point of my talk, so we're just put it forward there, and a lot of this was talked actually throughout these last 2 days, and the one is that elemental abundance evolution is that key part of metallicity evolution, but it's a really complex problem. I'll see if I can condense it down into 3 stages. One is a definition problem. Stellar abundances, they're not the same as gas abundances. We have different definitions, we measure different things, they're produced in different mechanisms, core collapse supernova, type 1a supernova, all the things Jackie talked about earlier. We have different time scales. But one of the biggest assumptions is that we tend to assume that the universe has solar-scaled chemical abundances. And so when we move to the high redshift universe, or things that are 10%, 1% solar, we just take what we see at the sun, or take alpha-enhanced elements, and we just scale these things uniformly down with what we see in the sun. And the problem with that is that elements, again, don't scale directly with metallicity. They can work tilde modulo fairly well. For example, in the blue, we have neon to oxygen, and then in the gold, we have argon to oxygen as abundance of gas phase abundances, and they work fairly well. But as was introduced yesterday, this doesn't work well for things like nitrogen and oxygen as a function of our gas phase abundances. And this is because nitrogen can have 2 different nucleosynthetic synthetic production mechanisms. So at low metallicity, it's primary, so your amount of nitrogen doesn't depend on the metal content of your star. At high metal content, the amount of nitrogen we see scales with the metal content of the stars. So we simply can't get what we see in the sun, which is the little blue dot, and just scale everything uniformly along the x-axis to go and see, okay, what would the nitrogen content be if we evolve stars with this type of chemistry at 10%, 1% solar. So then the question that we want to ask is, okay, so what would happen if we stop using relative abundances. I'm assuming this is okay. I have something that popped up, but I will keep going. What happens if we stop using relative solar abundances in star and gas models? And my last, really to drive this home, is because if you can't predict the chemistry of your stars and how much of a relative element you have within that star, you then also can't predict the observed emission lines you see from the H2 regions. And this manifests itself in a quite serious way. And I'll just show this as an example where we have sulfur 3 to sulfur 2 ratios as a function of sulfur 3 to O3 on the bottom axis. And the red and black contours are H2 regions in whole galaxies, and the colored point are grids, predictions from things like cloudy or mappings. And there's a huge mismatch between the two. And so what this is telling us is that we can't model and trust the ionized continuum coming from the massive stars that are powering these H2 regions. And so if we can't do that, how can we predict our emission lines? So the way we go about this is to just, say, see if we can quantitatively constrain that impact of solar scale chemistry. So we just move away from this problem, we go to the Milky Way, and we'll take O and B stars, and then we will measure the bulk trends of all the first 30 relative elemental abundances as a function of metallicity. You get a unique functional form. And then we just feed this into stellar evolution models where we use MESA to do this, and we do this for massive stars, not quite as massive as Jackie was talking about. I stop at 300 solar masses. We do it for rotating. We go down to slightly less than 1% solar content. And if you're not used to looking at HR diagrams, luminosity as a function of effective temperature of very massive stars, you're going to see that these little dancing elephants, the only thing that's happening the only difference between our non-solar scale abundances in purple and solar scale abundances is the chemistry. So we're using the exact same inputs into MESA, and there is a huge substantial difference in how we're going to interpret how these stars evolve. And this also has really important implications for how you can get luminous Wolf-Rayet stars at really low metallicity, because you simply can't do it, and it's difficult to do it with solar abundances at low metals, but you can do it with the non-solar scale. But you take your stellar tracks, we're going to combine them with stellar atmospheres in our stellar spectra, and then this will, we'll make assumptions on your IMF, on our star formation history, and this will spit us out a composite stellar spectra using programs, codes like SLUG, Starburst 99, or FSPS. And then all these things, our chemistry and our composite stellar spectra libraries, we will go and feed in to things like mappings or cloudy, and this will generate our libraries of predicted emission lines from our synthetic spectra as a function of metallicity, as a function of different chemical compositions. We're not quite at this last stage yet, because this is actually a really hard and complex problem. It takes a long time, takes a lot of computer time to get here. And one of the biggest things that prevents a stellar atmosphere is one of our biggest things that we're trying to solve to get over this hump to get to the final problem. Okay, so to try to put this in a context that I think everyone here understands, because there's been a lot of focus at high redshift. And so if we return to that question of how important was the relative scaling of elements in the end. So here what we're showing is a plot of Q, our ionizing photon luminosity, as a function of age of our composite stellar star clusters. The pink is for solar stars, solar chemistry, and the black is for our non-solar scaled stars. For the solid line is photons that can singly ionize hydrogen. Our dashed line is photons that can singly ionize helium, and then the dot is doubly ionized helium. You can see at solar metallicity, the two relatively match. That's okay. The sun is actually the sun's pretty close to an average solar metallicity star. But it changes a lot, and it's very drastic when we move to 10% or 1% metal content of the sun. And so what the appreciation is how we interpret the underlying ionizing source from these models is wildly different depending on the chemistry of the stellar populations, because the only thing we're changing is chemistry. And the thing that's kind of scary is because imagine trying to study the reionization of the early universe, and we are having and we're interpreting our ionizing photon budget off by about 2 decks. And so it's a really important problem. But as was discussed Monday, we lack metal poor, so these are just all theoretical models, and we tend to lack metal poor massive stars to validate these theoretical spectral models, regardless of their chemical content. And so what we have recently gotten up 2 proposals, one to look at 2 stars, one in the LMC, one in the SMC at very low metal content, and we're going to go and just stare at these things for, close to 1 night with UVES for both stars, and then on the koala, using the koala IFU on the AAT 4-meter telescope for 8 nights to go. And so this is an example of data we just took from the koala. This is actually only 20 minutes. We've blown through 2 of our nights so far. We've only had 20 minutes of observations. That's okay. You can already see how nice looking the strong emission lines are. We're just hoping with the remaining couple nights we can go and really dig down to get the auroral lines. And so this will be both a test bed for fundamental end-to-end analysis of atmospheric modeling, which is something that we still really need to work on, atomic data, and also nebula geometry and pressure assumptions. And it actually has some super cute bonus science, is that the resolution that we see, because these are in the LMC and SMC, will allow us to see where the ionizing photons are escaping, because observations have told us that almost all H2 regions are leaking. But we don't know how, where, or why, and hopefully this will help us answer that question. So then we can make assumptions. Oh, here, let me not quite show you that plot yet. I know how to put it in a movie. We can make assumptions on the yields of all the different elements, and then we can make assumptions on their IMF, and then you can take large star-forming complexes and you look at the variation of all the individual elemental abundance variations across the star-forming complex, and this allows you to constrain the relative importance of mixing versus your star formation history, or how long your bursts of star formation propagated through. Now, the problem with that is spectra is really expensive. I mean, you saw on my previous slide, we're observing 2 stars, and it's taking us close to 10 nights to get our data. And so most of our star cluster stellar populations in the universe, what we have is using broadband photometry. So we don't have spectra, and we just have to collapse everything and then infer our properties. And then it's made even worse by the fact that our ability to identify star clusters at a given mass is a very complex function of age as well. And then we're also limited by a completeness of where star clusters exist. There are very old, low mass star clusters. We just can't observe them, well, without infinite telescope time. And so you don't know the true underlying distribution of the star cluster population. But they still contribute to the ionizing photon budget. And so this is actually more of a computer science problem. So I have a graduate student, Janet Tang, who's working on a novel Bayesian forward model method, which obviates that need to assign unique masses and ages for every individual star cluster, and you don't get to then remove that need to the inevitable information lost. And so then if you return to the question, and the thing that we keep asking ourselves is, okay, when we have our global unresolved stellar population properties, how much does the chemistry matter in our interpretation of these photometry? Because this is what we have. We don't have nice, expensive spectra. We have photometry. And the question is, we don't actually quite know this yet. And what I'm showing you here are, for NGC 628, from the LEGIS catalog, luminosity distributions in the UV, UB, V, and I. Don't worry, I have 10 more seconds, and I'll be done. In the blue is showing the observed luminosity functions, and the green is showing our missed tracks using mass-independent disruptions. Data actually don't warrant the fact that there is a dependence on mass with cluster disruption, and the red is showing Padova. And the fascinating thing is that we've learned is you can go to super fancy stellar models and stellar tracks that use the state-of-the-art innovation, everything, and we're actually not doing a great job matching the tail ends of our observed luminosity functions in clusters. So there's still work to do. There's still a lot of work to do. And I will end it at that. Sorry.
Thank you very much, Katie. Questions for Katie? Is there anything online? No. I'm sure. Daniela.
Okay, I'll take the spot if nobody else wants it. So, what assumption do you have for the luminosity function there?
What assumptions are in there?
Yes.
Oh, all the assumptions, Daniela.
No, I mean for the cluster mass distribution, sorry.
So we are still using, so the original data used the Schechter fit, and so we have actually removed it to be a piecewise linear fit to remove the fact that, because what if it doesn't have a Schechter fit? But for the sake of comparison, we have adopted all the same properties that ran the original catalog, library catalog, to match the Adamo 2017 star puzzle.
Right. No, I mean for the models, do you have a slope of -2 at the high end or not? Because massive clusters in massive galaxies, they tend to have a cutoff at the high luminosity. So I was wondering if you had tried to reproduce that.
We get a slope that's very similar. I think it's -1.8. But it happens at much lower masses than what was originally found in the Adamo 2017 paper.
Okay, well, thank you, Katie. I think we should move on to the next talk now. So thank you again. Okay, so our next speaker is Massimo Pascal, who is going to tell us about nitrogen-enriched, highly pressurized nebular clouds surrounding a superstar cluster at cosmic noon.
A bit of a mouthful.
Yeah. Okay, so you've got 12 minutes. You should get to your conclusion.
Can everybody hear me okay? Yes? Cool. How does this work? Cool. Okay, well then let's get started. Hello everybody, I'm Massimo Pascali. I'm a graduate student at UC Berkeley. Today I want to talk to you about the chemical self-enrichment of superstar clusters at cosmic noon. And now to get all the way out to cosmic noon, we're going to make use of gravitational lensing. Specifically, we're going to look at the sunburst galaxy, which has been stretched out and beautifully multiply imaged 12 times. And that stretching that we get from the magnification allows us to resolve out individual star-forming clumps within the galaxy, as well as boosting the signal to noise to get very high-quality data. And so this is resolved out and afforded us 2 individual case studies of superstar clusters that exist within that galaxy. And so the first one that I'm going to talk about just briefly for a point of reference is the famous Lyman continuum leaking cluster, which as per the name is leaking out significant ionizing flux, and I think Brian talked about it earlier. And so we did global photoionization modeling of this cluster last year, and we found that it was very young, consistent with the ionizing flux being about 3 megayears in the stellar age. The metallicity was subsolar, around SMC-like, quarter solar. And we also found that it was very massive, 10 to the 7 to 10 to the 8 solar masses, all contained within about 10 parsecs. And so a number of other people have done completely independent analyses and found that these findings are quite robust. Everybody's in strong agreement there. We also found that for this superstar cluster, it was surrounded by a nebula that was significantly pressurized, such that it had very high electron densities, and this was probably pressurized by very high radiation pressure that it was seeing from the stars. And we also inferred that the nebula was likely some ordered or unity fraction CNO processed material from massive star winds, because we saw extremely elevated N over O. And so what the focus of this talk is going to be is a second superstar cluster that we found in the same galaxy, which has been named Godzilla. I did not name it. This is Godzilla here in the green, and you can see that I've marked the Lyman C cluster and its multiple images. And so this is where Godzilla begins to get kind of curious. Purely in the lensing effect, you'd expect that since you see this bright image of Godzilla, that you'd see other bright images of it similar to this Lyman C cluster, which I pointed out earlier. And so lensing experts have deduced that it's likely anomalously lensed somehow, potentially very highly magnified, factors of hundreds in the magnification for this individual superstar cluster. When you take into account the astrometry to measure the size, this would imply something of a couple parsecs in size. And so when you look instead from the photometry now to the spectroscopy, you see the spectral features are consistent with what you'd expect from maybe some young superstar cluster that contains a nebula, but with a number of oddities that I'll get into. And so the first thing that we'll focus on is the UV stellar wind feature, specifically this carbon 4-1550 P Cygni feature, which is typically indicative of having massive star winds. And so Godzilla is in the red, and then this Lyman C cluster I mentioned earlier for the point of reference is in the blue. And so what's interesting about this feature is that the redder emission component is sensitive to the age. So you can see that Godzilla is weaker than the Lyman C cluster, so we'd expect it to be older, so probably older than the 3 to 4 megayear age that I had deduced earlier. And then looking towards the blue in this broad absorption component, that's typically sensitive to the metallicity. And you can see they're in pretty good agreement, implying that they're probably around the same stellar metallicity. Of course, that's to be expected. They're in the same galaxy. We also don't see any detection of the broad helium-2 wind feature, which would usually be indicative of something like WN stars or some young, very massive stars that you might not expect at older than 3 to 4 megayears of age. And so now moving to the UV nebular features, we see strong detection of nitrogen-3, which of course indicates probably elevated N over O, which we'll revisit later. We also see strong UV oxygen-3 doublet. So this is of course a crucial doublet for getting things like the metallicity as well as inferring the ionization parameter. And then we also see these carbon-3 and silicon-3 line doublets. And so by the non-detection of the bluer part of this doublet, you can actually put a lower limit on the electron density, because these are density-sensitive line ratios. And you already get the electron density has to be greater than 10 to the 6 per centimeter cubed, so incredibly dense, right? And we also get some other detections of things like O2 and helium-1, which I'll talk about later. So when you move to the optical spectrum, I think this is where the nebular features get very interesting. And so here you're seeing the X-Shooter spectrum presented by Vanzella and colleagues 2020. And so you can see that Godzilla, which is marked here, has detection of neon-3, and yet it's quite noisy, but there's really not detection of strong H-Balmer lines, nor is there detection of the oxygen-3 optical doublet, which you typically expect to be quite strong, right? And so this sort of begs the question, well, we saw in the UV all of these strong lines, right? We saw strong UV oxygen-3. Why aren't we seeing the optical counterpart? Why aren't we seeing strong Balmer lines? Kind of adding to that curiosity. And then finally, we see this odd Lyman alpha pumping of iron-3 lines. So this has actually only really been observed in Edikar, as far as I know. Requires significant detuning of Lyman alpha, not consistent with the velocity dispersions we measure in the lines. And so maybe there's some way to trap the Lyman alpha such that you can get some significant detuning while keeping it very strong, but also not destroying the Lyman alpha. And so we're going to touch on that a little bit later. And so to better understand this curious physical picture, we're going to do some global photoionization modeling to infer the physical parameters of this cluster. And then hopefully that'll give us a better understanding of what's physically going on to create all of these things. And so here's sort of the flow chart of how we do that. We have some incident stellar radiation from BPAS, which is characterized by some metallicity as well as some age. We're going to feed that into cloudy, which is going to characterize the nebula with some pressure as well as some ionization parameter. And you can have multiple clouds, just like the home run talk that was yesterday. And then after that, we're going to do some post-processing to apply things like ISM dust reddening. We're going to take into account the nebular geometry, things like the covering factor, or how much of the illuminated face of the nebula versus the shaded face of the nebula you're seeing. We're also going to allow for some abundance rescalings for elements that we're sensitive to, things like carbon, nitrogen, neon, and silicon. We can infer all of those abundances using this. And so we're going to fit that to HST photometry as well as emission line fluxes from ground-based spectroscopy. And this is going to be some global fit that's going to allow us to infer the physical parameters of this system. And so right off the bat, this modeling gives us some reassuring results on the stellar parameter side. So I mentioned before from the wind features, we really expected it to probably be older than 3 to 4 megayears and to be SMC-like metallicity. And we recover those things despite not using the wind features in this modeling. We also find that it's quite massive, about 10 to the 6 solar masses, and keeping into account that astrometric size, so all of that's really down into a couple of parsecs. And we also see fairly low dust reddening, so these clouds might not be significantly dusty. On the nebular side, we see very low ionization parameter, minus 2.5, which might seem odd, but when you take into account that we see huge pressures implying very large electron densities greater than 10 to the 7 per centimeter cubed, it starts to make some sense. And of course, this starts to collisionally suppress that oxygen-3 optical doublet that I talked about earlier, sort of solving that one mystery of why that would be so weak. On the geometric side, we have this viewing angle parameter that chooses whether or not we're looking mainly at the illuminated versus the shaded face of the nebular clouds. And so what it prefers is that we're seeing entirely shaded face, such that the H2 emission is really going to be traveling through the full neutral column to our eyes. And that's what it prefers because there's significant optical depth to the Balmer lines, which is going to weaken those H-Balmer lines. And so that solves that mystery. And then finally, moving to the chemical abundances, following from that, the strong nitrogen-3 that we saw, we of course see fairly elevated N/O compared to the solar ratio. But what's interesting is that we see deficiencies in carbon, neon, and silicon with respect to oxygen. And so this clued us that maybe instead of seeing deficiencies in those elements, perhaps we were seeing enhancement in oxygen, such that maybe we were seeing core collapse supernova that were enriching the ISM. And so to further test this, we fixed the stellar metallicity to that SMC-like metallicity I mentioned before, and then we let the gas phase O over H and helium vary. And so we found that most of the parameters we had inferred were fairly robust to this, right? All of our abundances are mostly the same. You can see the purple and the black agree. However, we did find slightly higher, but still in good agreement, pressures and ionization parameters, implying overall huge ionizing fluxes and probably very, very small characteristic sizes for the clouds. And so in the O over H, we inferred about a factor of 4 enhancement, such that the O over H was similar to a solar abundance, despite the stars really being at SMC-like metallicity and this object being out at redshift 2. And then we also saw very broadly, loosely constrained some enhancement in helium. And so I think all of these nebular abundances really clue us towards the idea that we're seeing some ISM that's significantly enriched in both massive star winds as well as massive star supernova ejecta. And so what we did is we compared it to the Mola and Terlovich 2012 models. So they modeled the chemical abundances of accumulated ejecta of a star cluster across the cluster age. And so you can see the black lines is the theoretical prediction, the red swaths are what we measure for this object, and then the blue is the cluster age. And so with respect to hydrogen, our cluster age inferred, this is very consistent, right? So this could point towards this Godzilla cluster containing a nebula that's, some order unity fraction or purely just star cluster ejecta of both winds and supernovae. When you switch instead to with respect to oxygen, we see that indeed this enrichment by supernovae can explain the low C over O as well as the low silicon over O that we had inferred. Something that's a bit of an oddball, though, is the neon with respect to oxygen. Really, from the supernova, you would expect that these are kind of simultaneously produced and enriching the ISM, so it seems odd that you'd get something that's subsolar for this value. But given the cluster age, really we're only probing, if we are probing core collapse supernova ejecta, we're only probing it from massive stars, right? Stars that are more massive than 40 solar masses. So we wonder if this could have some implication for the neon to oxygen yields of core collapse supernova at these ages. As a quick test, we removed neon actually from the supernova yield, and that's what you're seeing in the dashed line. And it's actually somewhat consistent. So we're not saying anything strong here, but maybe this has some implications. And so taking all of these puzzle pieces together of all of these odd physical parameters that we infer, this is the overall physical picture that we come up with. So we have some superstar cluster out at cosmic noon. It's about 10 to the 6 solar masses. It's quite compact within about a parsec or a couple parsecs. It's likely somewhat mass segregated. We know this to be true for a lot of superstar clusters, such that most of the massive stars are in the center. And so over the first few mega years of its lifetime, the massive stars are going to be spewing out CNO processed ejecta, right, through their massive star winds. And at this level of compactness for the cluster, it's expected that these winds likely rapidly radiatively cool, such that all of that ejecta gets trapped within the cluster potential and sinks towards the center, and then it's sort of warmly UV heated yet self-shielded as it sits enshrouding all of these stars. As we approach 3 to 4 mega years, we expect supernova to start going off in these massive stars, and that's going to start driving a lot of turbulence in this cloud. And so that supersonic turbulence that's being driven can help explain the high pressures that we're inferring for this cloud, which was like log P of 11 to 12 for Kelvin per centimeter cubed. And then so within this cloud, right, we still have these enshrouded O stars. And these O stars have their own winds such that they're blowing small bubbles within the cloud. And they're moving relative to the cloud as well, so they experience some headwind. And so that allows you to get to even higher densities while getting something that's a very trapped geometry. I mentioned before that we favor seeing entirely the shaded face of the nebula. This would allow you to do that, right? You have some 100-ish AU bubble, but you're really only seeing the emission from the interface of that bubble, and then it's traveling through the neutral column. And then finally, this trap geometry also would allow you to trap Lyman alpha, assuming that there's not significant dust that would destroy it. This could explain that very odd Lyman alpha pumping fluorescence phenomenon that I had mentioned before. So we developed this physical picture really to answer all of these very odd things like high pressure, this preference for only the shaded face of the nebula, as well as probing mostly just core collapse supernova and massive star wind ejecta, right? Because this cloud is initially massive star wind ejecta, and then the supernova inject their material into it as well that all mixes around. And so you'd expect that the emission that you see from this interface would really be probing abundances that are indicative of that. And so what are the overall takeaways from the Godzilla and its nebula? So Godzilla is very young, it's very compact, it's quite massive. And so, from the theoretical side, people really aren't sure whether or not at the onset of supernova, whether supernova is going to clear out all of the gas or whether, it actually might be able to be retained in the cluster. And I'd say this is strong evidence that we've seen now a superstar cluster that's able to successfully retain not only its massive star wind ejecta, but also its massive star supernova ejecta. And so if you're interested in the chemical evolution of superstar clusters, in particular how they might evolve into something like globular clusters, I think this is particularly interesting, right? Because we see this enhancement in oxygen due to the supernova, we see enhancement in helium due to the massive star winds. This wouldn't be consistent with what you'd see in the 2P populations of globular clusters. And so we managed to squeak out this paper on the archive yesterday, so you can go ahead and scan that QR code if you'd like to see more. Thank you very much, everybody.
Thank you. Very interesting object. Questions? Oh, lots of questions. Okay, there's 3 hands up over there.
So I'm really intrigued by the high densities that you're inferring in the hot phase to pressure confine these clouds. And I'm imagining that it might actually be pushing into the range where the X-ray emissivity is high enough that you have a chance of detecting this directly. Is it actually feasible? Do you have constraints on it?
So there is quite deep X-ray or the Chandra data on this object, very deep actually. I don't know how they got that much time. We didn't see anything. I think part of it is that you have to deal with the bright cluster foreground, right? This is being lensed by a galaxy cluster. And so you have significant X-ray background. So I'm not sure, but observations have yet to yield anything on that end.
Thanks, Massimo. Super interesting. I wonder if you could clarify something about the geometry that you've proposed for this. So it wasn't clear to me how it explains significant attenuation in the Balmer lines, but almost no reddening for the stars.
Right. So I think this gets a little bit complicated because it has to do with sort of the trapping of Lyman alpha that elevates this sort of n=2 population, which then allows you to get resonant scattering of the Balmer lines. I think they studied this in the 80s a lot, like Ferland and Netzer. 1979 is probably what you'd want to look at. But yeah, we definitely had to dig deep to understand this.
Got it. Got it. Thank you.
Okay, time for one last question. I think there's a hand at the back. Yeah.
Yeah, thanks. This is really cool stuff. I was curious, the Diego et al. Paper that you mentioned that nicknamed it Godzilla did so under the assumption that this was a single star that was extremely magnified with a magnification in the thousands. And that's obviously inconsistent with something like a stellar mass of 10 to the 6. But these parameters are, of course, magnification dependent. So I'm wondering first of all, what magnification are you assuming? And then second of all, are you seeing any other features that are sort of more directly indicative of this being a star cluster versus a single star? In particular, I'm thinking things like this. You mentioned Eta Carina as an analog. This could be something like Eta Car that's extremely magnified, or something more like this cluster that you're mentioning that's at a lower magnification. Could you comment a little bit on that distinction?
Yeah, definitely. So that's a good catch. So just for context, so in the original paper that named the cluster Godzilla, they had placed some sort of dark matter subhalo near the object and had inferred that the magnification could be as high as thousands. I think from the lensing theory side, it's maybe difficult to reach those levels of magnification. Of course, Brian has seen that firsthand, though, that we can do that. And so if you take that into account, you might want to explain it with something that's a lot more compact. But that paper didn't really explore the nebular features very much. I think just given that, when we compare it to a known superstar cluster like the Lyman C cluster, let me see if I can go all the way back. as well as other parts of the arc. So we actually have in the black sort of unremarkable parts of the arc. It just seems so consistent with what you'd expect from a star cluster as opposed to maybe an individual star. That I really think star cluster is the most probable explanation for what's going on.
Okay, I think we have to move on now, so thank you. Thank you very much.
Thank you.
Is magari lo puoi tenere in mano e questo metterebbe magari da che parte bisogna mettere.
Okay, so our third speaker is Ambra Nani, who's going to tell us all about unveiling cosmic dust chronicles at early epochs with JWST. Thank you. And this is going to start. And so look at it, and when you get to 12 minutes, okay, you're done.
Okay, thank you. Can you hear me? Can you hear me well? No.
Have you got it switched on?
Is it on? Yeah.
Can you see? Yes, it's on.
Yes, yes.
Where is?
I see.
Speak again.
Okay. So it's. Can you hear me well now? Okay. Okay, thank you, and thanks to the organizer to giving me this great chance of talking about the dust at early epochs with the JWST. I'm Ambra Nani from the National Center of Nuclear Research in Warsaw, and these are my collaborators, and I underline the people that are here today in the room. So I don't have to convince you that dust in space is important. We have that dust shapes greatly the spectral energy distribution of galaxies by absorbing the UV and optical radiation and remitting it in the infrared wavelengths. This is important also at high redshift, and now we have the possibility to look into spectra of high redshift galaxies. I will focus in this talk about these galaxies at redshift 6.7 observed by JADES, so the JWST Advanced Deep Extragalactic Survey. And what's special about this galaxy? So we have that this galaxy basically has a very deep absorption bump at 2,175 angstrom. And this bump indicates the presence of small hydrocarbons, so polycyclic aromatic hydrocarbons. And this bump is quite deep if we look at it in the right panel. So here we have the bump amplitude as a function of redshift, and we can clearly see that the bump amplitude is comparable to the one of the Milky Way already at redshift 6.7. Okay. So besides having this bump, we have also the evidence of dust extinction, dust attenuation through the measurement of H alpha over H beta of 3.7. And we have also strong oxygen line indicating a metallicity of about 1/3 solar. Okay, and so we want to explain these observations, and in particular, we want to understand the fast metal and dust enrichment of JADES galaxy, constraining the star formation history, or at least having an idea of the star formation history by studying its baryon evolution, and reproduce this bump that we observe and constrain the pH's abundance. So method and tool, we use the Pegas code. In particular, we know that we need a stellar population synthesis code. We need to assume something for the star formation history and the initial mass function. We have that the code follow consistently the metal evolution. And for the dust part, we have dust evolution. We have dust optical properties that are consistent with the evolution of dust in the ISM. And we have to assume something for the dust geometry. So combining this information, we can obtain the full spectra of our galaxy and compare it to the observations. So these are the models that we use for the metal and dust evolution in the galaxy. Basically, we reformulate a little bit the ingredients that we have in the Pegas code by including a better treatment of the destruction timescale of supernova with the mass web by each supernova event that is depending on the metallicity, and the accretion timescale of dust in the interstellar medium that is related to the metallicity. We assume a Chabrier initial mass function. We also tested a top-heavy IMF, but the results are too preliminary to be discussed, so I will focus on the Chabrier IMF case. Okay. So I was mentioning that we have to assume something for dust geometry, and basically for doing this, we started from the stellar surface brightness observed through the 356 filter from JWST, and we derived the stellar surface brightness profile, assuming a King model. And from this, we derive the main parameters such as alpha, truncation radius, and core radius. And starting from this, we assume something for the dust distribution, and in particular, we assume that we assume the same King profile, but with alpha multiplied by a factor with respect to the stellar case. And this factor is between 0.5 and 2, depending on the model. Okay. So we tested different star formation histories. Here I'm showing some examples. So this star formation history is the delayed star formation history. We constrained the tau, that is around 1,000 mega-year. And these are, in the right, you can see two cases for the results. In particular, we have the case, the orange line is the case with low condensation of metals into dust for type 2 supernova. So we have 10% of metal condensed into dust. And we have a dust accretion in the interstellar medium. On the other end, in the other case, we have an high condensation fraction of metals into dust for type 2 supernova, around 70%, and no dust growth in the interstellar medium. So we see that the attenuation in both cases is not so well reproduced because the H alpha over H beta is around 3.2, whereas the observed one is around 3.7. We have a good fit of the oxygen lines, and the UV slope is better reproduced by the case in which we only have a supernova dust. And the bump is reproduced with a 4% in mass of PIHs. Okay, if we look better into the models, we can see better how they have been built. So we see the case with just type 2 supernova and the case with type 2 supernova and dust growth in the interstellar medium. We see that dust growth becomes efficient already at 60 mega-years, so it can really contribute to the dust growth, to the dust production in galaxies. We reach this more or less the same final values. So the thing is that we cannot really distinguish between the two scenarios with the present data we have. In this scenario, we have a fast enrichment of dust in the interstellar medium, which takes about 150 mega-years. And I didn't even plot the contribution of AGB stars because it was out of the plot, basically, because it's too low. They don't have time to efficiently contribute to the enrichment of the galaxy in this scenario. So second scenario is delayed star formation rate with tau 100 mega-years and a burst after 600 mega-years. In this case, we have that the attenuation is better reproduced also because we have more time to produce dust and to have an efficient dust enrichment. Also, the oxygen lines are reasonably well reproduced. We need a young burst because we need to reproduce the UV slope, otherwise it's not possible with this dust enrichment to have the right UV slope. And the bump, again, is reproduced with 4% of PIHs in mass fraction. So if we look at the models, so here I just consider the case in which I have supernova dust condensation fraction of 10% plus dust growing the interstellar medium. And in this case, AGB stars can contribute more with respect to the previous case because they have more time, but still they seem to be a secondary contributors to the overall dust enrichment of the galaxy. We have more time, so we have that the dust production occurs in 600 mega years, but this requires also to form the galaxy quite early at redshift of 18, and the bump is still reproduced by 4% in mass of PIHs. So we know that in the local universe there is this relation between the mass fraction of PIHs and the metallicity. And this is from Dustpedia and DGS local galaxies. And if we compare with our result, basically we find that the mass fraction that is needed to reproduce the bump lies on the same relation with the metallicity as the local galaxies. So we put it into a larger context by comparing the results with the alpine sample at redshift between 4 and 6, even if you cannot read there, but trust me. And so we compare with this sample of star-forming normal galaxies. Here we have this diagnostic plot that is specific mass of dust, so mass of dust as a function of the specific star formation rate, so star formation rate over stellar mass. Okay, all these models, the details of all these models you can find in Prasad Sawant poster, so speak with him. And if we put again our galaxy here, we find that it looks like a little bit of an outlier with respect to alpine galaxies, but this may depend on the way we derive the mass of dust, since we don't have any constraint on the continuum of the dust. So it may be that the way is derived is too crude to have a good estimate, but we have to see. So these are my conclusions. We have tested different possible scenarios for the star formation history of this galaxy observed at redshift 6.7 by JWST, a delayed and a delay plus burst, but also other options are possible, for example, multiple burst. I didn't mention that I have to form a lot of stars in the burst, about 40% of the total. So it's a huge amount to reproduce the UV slope. The case with delay plus burst seems to better reproduce the dust attenuation and the steep UV slope. There is degeneracy between the scenario with dust production from efficient dust production from type 2 supernova and having a lower efficiency for dust production in type 2 supernova, but grain growing the interstellar medium. So because grain growing the interstellar medium becomes efficiently quite quickly. AGB stars are, in these scenarios at least, are likely to be the major enrichers of dust in the interstellar medium. And the 2165 Armstrong bump can be reproduced with, yes, I'm done, with a mass fraction of PIHs around 4% compatible with local galaxy. Thank you.
Okay, thank you very much. Questions?
Thank you. Really nice talk there. Are you considering looking at other star formation histories going forward? And if so, have you got any ideas? Because there seems to be quite strong H-alpha emission, which would suggest that maybe if there was any bursts, there might be, I don't know, occurring on much smaller timescales compared to what we're seeing in the kind of bursts in the star formation history, you know, of the order of 10 mega years or so.
Yeah, I mean, I can choose to have a longer burst, for example. I can also use different star formation histories, such as I was thinking about taking something from cosmological simulation and input in the models that I'm using. But yeah, we have to see. And yes, basically I consider these two scenarios because in one you have a fast enrichment and in the other one you have a slower enrichment, but you need this fast production of stars at 1.2, have this UV slope. But I can also have a milder burst, let's say, so with the same amount of stars, but not so peaked, so more like smooth.
Maybe a non-parametric model could potentially help with smoothing out over a longer time scale.
Yeah, okay.
Thanks very much.
Okay, well, let's move on then. Let's thank our speaker again, and we'll go to the last talk. Okay, so the last talk before we start the discussion. Gosh, you've changed the title.
I know, I'm so sorry.
No, it's all right. It's by Anna Engelhardt, and it's Bursting with Feedback, Exploring Models of Star Formation and Stellar Feedback at Small Scales. Thank you. Oh, yeah, that's the timer.
Thank you. All right, so hopefully everyone can hear me. My name is Anna Engelhardt. I'm a graduate student at George Mason University and a part of the larger N-Body Shop collaboration. Before I get started, I would like to give a quick thank you to NASA for funding me through my finance fellowship, as well as my research advisor, Dr. Farad Munshi, and my collaborators that are all listed on the slide, one of whom is also with us in this room. Let's see. All right, so my talk is divided into two separate sections. The first tries to answer the question, how do subgrid supernova feedback models impact the burstiness of star formation? And I'm doing this by looking at two different models of supernova feedback and doing a direct comparison with, within the same suite of simulations. And the second half of my talk will try to answer the question, how sensitive are the star formation histories of ultra-faint dwarfs, or UFDs, to subgrid star formation models? And the reason why we care about the star formation histories of UFDs in particular is because at these extremely small masses, galaxies are unable to self-regulate, making them much more impacted to choices in subgrid models and different parameters that you input into your simulations. So I'm presenting a sample from STORM, which is one of the 4 Marvelous Dwarf N-Body SPH simulations run with Chang'e. The resolution is all written up on the slide. And here in the video, we're just zooming in on a small Milky Cloud galaxy simulated from Captain Marvel, which is also from the same suite of simulations with dark matter density on the left-hand side and gas density on the right-hand side. So the two different supernova feedback models I will be comparing today are blast wave feedback and superbubble feedback. In blast wave feedback, we artificially turn cooling off for the duration of a snowplow phase in our supernova gas-heated particles. And superbubble introduces a thermal conduction and subgrid evaporation to regulate the quantity of supernova heated gas at any given time step. To the right, we have the stellar mass-halo mass relation with our superbubble galaxies in red, our blast wave galaxies in blue. The black lines link galaxies with dark matter halos, which have a certain number of shared dark matter particles above a specific threshold. And as you can see, our data points are generally well constrained by the fits from Nadler and Jethwa. And also on the slide, you can see the QR code, which will take you to the paper that I'm a co-first author on, which shares these results along with a number of other ones from this presentation. And then I also put the GitHub link up on here if you guys want to take a look at how we calculated these properties as well as how we made the figures. So now we're looking at the cumulative star formation histories of each individual galaxy in our sample. Blast wave galaxies are on top, galaxies simulated with superbubble feedback are on the bottom, and they're all colored by stellar mass and divided into different mass spins. As you can see, the bright dwarfs tend to have a more continuous and extended star formation history, while our ultra-faint dwarfs are typically forming and also quenching at extremely early times. So they have extremely short bursts of star formation. And then our classical dwarfs can actually experience a wide range of different star formation histories. Though what we're also seeing is that the star formation histories produced by both superbubble and blast wave feedback seem to be pretty similar. Here we're looking at the mean burstiness versus the stellar mass-halo mass ratio. Our burstiness calculation is done using the equation on the right-hand side, where we're taking the standard deviation of the supernova rate divided by the mean of the supernova rate. And the reason why we're using supernova rate in this case is because it tracks star formation rate pretty well. And a value of 0 represents a uniform distribution, while a mean burstiness of -1 represents an exponential distribution. As you can see, our ultra-faint dwarfs are generally having a more exponential distribution, while at higher masses, we see significant increases to the burstiness values. And then the other kind of main takeaway from this figure is that the maximum burstiness that we see is happening at a lower stellar mass-halo mass ratio with superbubble feedback compared to blast wave feedback. Here we're comparing the core slope versus the stellar mass-halo mass ratio. A core slope value of 0 represents a chord central dark matter density profile, while a core slope value of -1 represents a cuspy dark matter density profile. We're comparing our results with halos from fire in the triangle, as well as some dark matter only halos with the black X's. If you simulate galaxies using baryonic feedback, you get core production, and then we're also seeing that for both superbubble and blast wave feedback, we're getting peak core production occurring within the kind of same stellar mass-halo mass ratios, where we also see a peak in burstiness values. So where we see core formation effectively happening and where we see mean burstiness maximizing is in the same kind of range of stellar mass-halo mass ratios. Now I'll get into the second half of my talk, where I am presenting a sample from Sandra, which is one of the 4 DC Justice League simulations. These are also N-body SPH simulations run with Changa. Resolution is written up on the slide for you guys to look at. And I'm comparing 4 different models of star formation. So the first model of star formation that I look at is an H2 model, where star formation is based on the non-equilibrium abundance of hydrogen. And then we're also looking at a low density threshold and a high density threshold model, where we're implementing a simple temperature and density threshold above or below which star formation can occur. In the low density threshold, this is 100 AMU per centimeter cubed. In the high density threshold model, this is 1,000 AMU per centimeter cubed. And the last star formation model we're looking at is SHIELD, where star formation depends on the dust shielding of gas. So looking at the cumulative star formation histories from each model, where H2 is in blue, MC is in green, and this is the low density threshold. SHIELD is in orangey red, and then MC1000, which is the high density threshold, is in purple. We see that for both the H2 and the SHIELD models, we have a more extended and continuous star formation history, while the MC and MC1000 models typically are forming all of their stars within a single burst, and they also are maybe a bit more late forming relative to the SHIELD and H2 models. Here we're looking at the phase diagram of star formation in each of our different models. So we get this phase diagram by taking the temperature that each star, the temperature and density of each parent gas particle the moment it's forming a star particle. And our H2 model forms stars at the highest densities and lowest temperatures, with the MC and MC1000 models tending to form stars at typically just above the implemented density threshold. With the exception of MC, you see that there's some high temperature stars that are forming at a bit more of an extended or lower density. So now on the left-hand side, we're looking at the metallicity distribution functions of each of our different star formation models compared to observational results from Kirby. And the MC1000 model in this case seems to be the best fit to what we detect observationally, though the H2 model does have this is centered on the same average metallicity value, while the width is just a little bit lower or smaller. And our SHIELD and MC models tend to have a little bit lower metallicities. And then looking on the right-hand side, we're plotting the spread in metallicity versus the visual band luminosity. And in this case, we're comparing our results with observations from Simon, and most of our different models are fairly well constrained by observations, with the exception of our H2 model, which experiences a significantly higher spread in metallicity. And kind of the main takeaway that I want you guys to have from this slide is that the width of the MDF in particular seems to be a potential great discriminator between different star formation models. So the conclusions are that both the blast wave and superbubble mechanisms produce dwarfs, which are well constrained by observations. Higher mass dwarfs have burstier star formation histories and efficiently produce central dark matter density cores. Low mass galaxies form the majority of their stellar populations in 1 to 2 concentrated bursts of star formation, and they also retain cuspy central dark matter density profiles. The metallicity and star formation histories of UFDs are extremely sensitive to star formation prescription, and the width of an MDF is a pretty good potential discriminator between subgrid models of star formation, specifically in UFDs. And let's see, I do have a bit more time than I expected because I talk very fast when I'm nervous. So we can also look at this figure that shows the average stellar metallicity plotted against the visual band luminosity for our different supernova feedback models. So this is going back to the same sample from the first half of my talk. And as you can see, our average stellar metallicities are pretty well in line with these gray points, which represent observations at higher masses. At lower masses, though, our sample, sadly, along with many of the other simulations out there, do struggle to reproduce high enough metallicities in that extremely low mass range. So that is something that simulations are actively working on trying to counter. Yeah.
Okay, thank you. Questions?
Hi, I have just a question about the thing that is a bit counterintuitive for me, which is the higher massive galaxies you find to be burstier than lower massive. I would expect the opposite, because usually lower massive galaxies have shallower potential wells and maybe more sensitive, while they grow in mass, maybe they become more stable. So if you can comment on that.
So I guess that kind of depends on like how you're defining burstiness. So I think that with our specific model, and it also depends on time scale, right? So we're performing our burstiness calculation with, I believe, looking at averaging over timescales of 50 million years. And so Let's see, I'm trying to put it into words. Basically, what it comes down to is that you're seeing star formation histories that are taking place over longer periods of times. So it's not all concentrated at one end. So the reason why the UFDs are so low is because it's literally just like one small burst of star formation. So it's extremely exponential. And then at that higher mass end, since the star formation is taking place over a longer time, you see that it's more continuous, but there's still some like fluctuations. There's still significant fluctuations like within that in terms of like star forming periods and like less star forming periods, if that makes sense.
It's basically that your ultra faint are so small that basically they have the very super simple star formation.
Yeah,
histories,
they
like single
turn
bars
off and then they
tendency.
turn.
Okay.
Yeah, they
I
turn
see.
on and turn off like immediately, which is why the values are so low.
Thank you.
Okay, well, let's thank our speaker again, and then we'll move to the next section. Okay, discussion time. I think, is it Katie and Ryan?
So, this is part 2 of yesterday's discussion. We had the Slido yesterday, but the discussion wasn't tip-top, and we don't know whether that was because you were burning desire to go to the baseball game and you were tired, or you didn't like Slido. So we're going to take a quick vote, a demographic vote. Do you want to do more Slido with discussion, or just talk freely without the Slido? Who wants to do the Slido with the open discussion? Come on. Okay, great. Well, Slido it is. If you log back into Slack, go to the general channel, there will be a link there. But the idea is to facilitate discussion with the Slido, not to just have your silent discussion on Slido. Okay? Do we still have it? Oh my gosh, please don't tell me. Did somebody shut the browser? There may not actually be a choice because I think somebody shut the browser and logged us out of Danielle's Slido. Yeah, they did.
Well, then that solves that.
That solves the problem. Sorry about the vote. Well, democracy doesn't always work, does it? So,
I need my questions on my laptop.
okay, well, I remember one of the questions was, we can just do a hands vote actually. Will we ever observe a POP3 star? The selections were yes, no, or not in my lifetime. So how about yes, who thinks we're ever going to observe a POP3 star? Okay. Well, there is an option for once in my lifetime. There's a not in your lifetime option, yeah. It's okay. So only a few people. That's hopeful, though. Obviously, who says no? We're never going to observe a POP3 star. Ooh, okay. And so who says not in my lifetime? Okay. Why?
Unless we get incredibly lucky with a caustic, they're too faint. Particularly if we're trying to go to really high redshifts, we're going to need a really, really big telescope, and I'm just hoping Habitable Worlds launches in my lifetime.
Well,
you know, which is fair. But unless we get incredibly lucky and there happens to be one that crosses a caustic that magnifies by a factor of 10,000.
Any more thoughts?
Well, that's a different question.
Yeah. Okay. Well, we can do that. We can do that one next.
My question was going to be like, what redshift do you expect it to see, right? Like, if you have low wow, you might see in the UV, but you're limited to some very low redshift regime then. So the question is perhaps like at what redshift do you expect to see them? What is the lowest you might see, right?
So I think the other question that's relevant is what is the POP3 IMF, right? Because if you expect that they're all very massive, then they're all going to be dead by now. But if we can form low mass, particularly subsolar mass POP3 stars, right, then you might expect that some could survive today. We might find them in our own galaxy.
As an additional caveat to that, if you have supernova that pollute the photospheres of these POP3 stars, are we going to recognize them as POP3 stars?
So 2 comments about the up to when we can hope to observe them. I want to mention that some simulation also predict that patches of pristine gas can survive up to redshift 4 or even 3. So maybe there's hope that a lower redshift we will have still formation of these metal-free stars. It's not that either we see them at redshift 15 or nothing. So, and maybe we should look for ways to maybe, of course, not catch single stars, but POP3 galaxies, so maybe clumps of populations of pristine stars forming together. But we need to, I think, actively look for tracers and key elements, or I don't know what, but not to wait for like luck to catch them in surveys. But maybe we need to figure out what are the key observables, elements, and stuff. So I don't know. I think we need to do an effort like that this summer.
Okay, well then we can latch onto that and then say, what are the observables of POP3 stars?
I don't know. Jackie?
So for all those who are like, yeah, yes, we'll observe one, what are the observables?
Helium-2?
I think it's hard.
Yeah, so POP3 helium-2, but I mentioned the parent-state supernova. That's slightly different question. In single star, the parent-state supernova can possibly come from zero metal stars. But with binary, it's actually possible to have parent-state supernova from slightly metal-enhanced area as well. So it's a bit complicated. Anyway, to identify the parent-state supernova, the key elemental abundance signature is a heavy alpha to oxygen ratio, and also alpha to ion ratio. So combination of these 3 can solve the degeneracy, can distinguish from the 1A or other channels.
But isn't that a problem that your simulation showed that you can have supernova ejecting oxygen? Because you can have that same effect by just removing oxygen from the galaxy, right? This is what we see in some of these EM, like very low metallicity systems in the local universe, where is oxygen depleted but ion enhanced. So I wonder if that'll be a problem or not.
So silicon to sulfur, the sulfur to oxygen is high because of large production of sulfur. And oxygen mass is still larger than quark supernova. So oxygen is enhanced by parent-state supernova. So in a nitrogen to oxygen diagram, with a pair, the nitrogen to oxygen ratio becomes lower, as low as the plateau value. So it's not good for GNZ11.
Before I put this out there, I just want to say I'm not an expert on POP3 stars or simulations, but just wanted to throw out there that I'm pretty certain there's been a lot of work to suggest that these like first stars that form POP3-wise are potentially direct collapse, particularly the first generation. So how would we be able to pick up those objects if they're direct collapse and don't go supernovae in the first place? And whether or not there's any consensus within the community with regards to that question.
Okay, we're gonna now move on to our next topic. This has all been great. And I'll start with asking you, Ryan, which is, so what do we need from high resolution local surveys and simulations, and how will this inform our assumptions about high redshift objects?
Yeah, so I think this is something interesting to consider, especially as we actually get spatially resolved observations at high redshift. We've seen different examples how modeling things as, sort of single integrated sources, like in photonization models versus multiple components that have different properties can really affect the outcomes. So I think there's some different things to think about. I think one thing, especially as simulations get very sophisticated, is how much of this can we process into observables that can be directly compared to observations instead of course, you can take your observables, go through models, translate those physical properties compared to simulations. How much more work can we do with simulations to mock observations to compare with things, especially with spectroscopy, which I think is more of a forefront for making mock observations. Anyone have more thoughts on this topic? Maybe not. What simulations do people want to see that might be missing from the current parameter space that we have?
I want very small scale simulations with density structures where you can take time stamps of of all the different phases of the gas that accurately show what the different elements are doing at different times, but within a realistic density structure with realistic feedback. Please. I guess size of a dwarf galaxy, but can take me down to the size of an H2 region, so 100 parsecs. It's easy, right?
Would one galaxy suffice, or you need many of them? That's the question, right? If we do it at very high resolution, then we can't do too many of them. That's just the bottleneck.
Got to start somewhere, though. So
that's true. I think some simulations actually can reach that resolution already. It's just that, do we want to track all these elements, species separately? And that will also add to the problem. So it's really hard.
It's possible, but not sure we can believe the results because when the resolution is improved, much improved, we actually don't know the star formation. So it's hit how we actually assume star formation. So for subgalactic scale, it's okay to assume chemical tilt low. It's okay to assume some average IMF integrated chemical enrichment. But if we really resolve stars, we actually have to think about exactly the star formation and IMF. So the result will depend on the assumption.
Well, we can change the question a little bit and then say, then what do we need from instrumentation?
We need UV IFUs in space.
And optical.
Muse in space, yeah.
So this is basically the habitable worlds thing that we're going to hear about tomorrow, right?
Oh yeah, exactly. Habitable worlds will be presented tomorrow, and then you can pitch to Jason Tumlinson what you want on your instrumentation list. So start thinking about resolutions, spatial scales, all the things. Do you want to? Yeah, let's have this will segue into a nice question to end this discussion on and maybe inspire some conversations during lunchtime. But imagine you had unlimited time on a telescope with unlimited possibilities. What would you do with it? If you could do anything, what would you want to see? What would you want to observe? What answer would you like to get?
Well, I can just perhaps. Oh, go ahead. Just to resolve stellar populations and get the IMF. right? Even nearby galaxies, to do as well as you can by separating stars and as a function of age and position and clustering and so on, because that is such a huge uncertainty.
I think given the scope of the question that you can do pretty much anything. It's, you know, as we're seeing now with a lot of this new web data, every time you go deeper with spectra, you find new lines that tell you something really, really important. And it seems like the things that we're trying to tease out that are the most important are always right at our signal to noise limit, especially with, for example, some of these, you know, recombination lines things. So I think go as deep as you possibly can and tease out details from those lines that you just can't get otherwise. I mean, really, the only limit is how deep your spectra are. You'll keep learning more the deeper you go.
I would say observations of the CGM in hydrogen and metal emission, so that we can understand what's really going on with the gas around galaxies, the distribution of metals, and the kinematics of these different phases.
If we're really talking about unlimited resources, okay. To figure out selection effects at high redshift, to actually be able to push deep enough to get both imaging and spectra back below the tip of the luminosity function above sort of a luminosity of 8 or 9, redshift of 8 or 9. I need more sleep.
I would say that the internal structure of these two regions, we still don't know. More of the information comes from the basic fixes we know from Orion, for example, right? But we observe only a small part of Orion. I know that there are a few data, but still there is a filling factor, a temperature structure, density structure, a star that we still don't understand about dust also. So many things about Orion, these heavy halo components. So we'll still need to constrain many of the basic fundamental fixes of nebula.
Carla, can I quick follow up? Given that we always have to observe, you know, projections along an entire sight line, can we really tease out all of that 3D structure with our limitation to observations in a 2D space? Katie says send the telescope into the H2.
Exactly.
Unlimited.
Fly-through telescope.
Yeah.
You only have to wait several thousand years to...
That can survive 10,000 Kelvin gas.
Okay, my strong desire would be pop 3 stars in my lifetime.
Any other burning? No, I think we're all now excited for lunch. I know I am. Okay, so we're gonna let everyone go 5 minutes early, which means you can go and spend 5 minutes after lunch perusing posters. Thank you.
Wait. One small announcement. Again, sorry. We have limited vegan, vegetarian, pescatarian options. So if you've not indicated that, maybe don't go for that option first. Yeah, we had some people running out of like those options yesterday. So thank you so much. We're all set for like this afternoon, right?